Thank you very much, Tavy. I'm now going to get out of my Zoom view and start talking to my slides. So I hope you're going to rescue me if anything goes horribly wrong, but here we go.
We will, of course. We will, of course.
Good. Right. Well, hello, everybody, and thank you very much for coming to the talk. And you'll realise that I spent a lot of trying to avoid Tavy and pretend that I didn't exist anymore, but she caught up with me, as indeed did COVID. Sorry for the comparison. So now it's my turn to give a talk in what has been obviously a fantastic series and a real transformation of the way we communicate in glaciology. When I thought about what I wanted to talk about, I decided that it might be good for me to stop and think about dry snow densification, because I had been struggling with a number of problems, and I realized that I didn't have a very coherent view of the whole of the field. I got my nose too deep in certain aspects, and it would be very good for me to stand back and try and take an overview. And I'm going to really focus on one very small aspect of the behavior of snow, which might seem like a very narrow topic, but it turns out that there really is quite a lot to think about and discuss. Why not? Okay.
Are you trying to advance your slide?
That's it. Okay, I've got there. Sorry about that. Well, okay, the idea is that this shouldn't be too heavy, and that we're going for a gentle overview of the subject, and it ought to be accessible for anybody in whatever field that you're working in glaciology. I just want to provide enough information for people to appreciate what the problems are and get a feel for how colleagues working in the field are going about solving them. So I hope that anybody who's a real expert is not going to get too impatient, because this is really for the general populace, as it were. So what I'm going to do is start by trying to define the problem that I'm interested in, then look at what sort of data are available to try and solve it, carry on to see where we are with modelling the physical processes involved using those data, and then the big question is, where do we go from here? And I should say that earlier this year there was a very stimulating online workshop on fern processes, and I gained an awful lot from that experience and want to thank the participants. But nevertheless, this is very definitely a personal view, for better or for worse. So let's define the problem. To simulate and predict the behavior of dry snow, we need a snow model, by which I mean a set of equations which relate the velocity, density, stresses and temperature and so on of the mixture, ice, water vapor and air. So that's what I mean by a snow model. And the equations are going to be the ones that will apply to any problem, the conservation equations for mass, energy and momentum, and then particular equations which apply particularly to snow, which are the constitutive equations. So I'm going to leave aside all the many and various difficulties in defining a dry snow model, and tonight I'm just going to focus on one of these equations, one constitutive equation, and that's the one which concerns the deformation that occurs because snow has been put under pressure. Of course, there are other equations which will describe densification because the snow crystals change shape and size under the influence of temperature gradients or radiation. But these other things I'm going to leave for another time. So it's purely deformation under pressure that I'm interested in. Now, a couple of things I need to define in order to be able to talk about things. First of all, being precise, what we want is a constitutive law which relates the strain rate tensor epsilon dot to the stress tensor sigma. And there's no need to have a stress alert for tensors, because all I'm doing is using a single symbol which will cover all the stresses and strains on a volume element, the normal ones, the shear stresses, and so on. The first thing we have to think about is the scale on which we look at the problem. Are we going to look at the scale on which the snow is essentially isotropic, which we might call the red box scale, or are we going to go to a larger scale, the blue box scale, in which the snow definitely has a structure, horizontal layering, for example? Well, looking at the simplest red box case first, just to define some terms. The whole point about the snow being isotropic is that it doesn't care about the choice of coordinates. And so we can start making some simplifications. For example, you could define a coordinate system in which Z is the vertical coordinate, and that's what I'll do. And X and Y are horizontal coordinates. But the snow is not going to care about this. So that the law that we're looking about is expressed in terms of groups of tensor components which are independent of the way we're labeling it. They're invariant. And the first thing to do is to separate out the stress and the strain rate into two bits. One is the deviatoric component and the other is the isotropic component, so that we can talk about stress and strain E dot and tau for the deviatoric part, and then we can talk about the sum of the strain rates and the pressure for the isotropic part. Now, that's pretty well all I'm going to need to say about what the equation looks like generally. We can write it as a compressible linear viscous fluid expression. And the only reason why I'm bringing this up now is because talking about the properties of the snow, since time immemorial, people have talked about the viscosity of snow, by which they mean the relationship between the stress and the strain rate. That viscosity does not have to be a single value. The important thing is that the zeta and the eta here, which are viscosities in the sense that they're the coefficients in a linear relationship, but it doesn't mean that they're independent of the stresses. In fact, normally speaking, we'd say that they're likely to be dependent on the second invariant, which I've shown below in the box, which is called the effective stress. The take-home message of this is really that if we're talking about calculating strain, we're likely to need all the components of the stress tensor in general. Right, that's enough maths. I hope all I've done is just tell you not to worry about the term viscosity. It's just a relationship between stress and strain rate. Well, let's begin with the most obvious and simplest test that can be done, and that's to take a snow block rested on a solid surface, put a weight on top and measure the vertical strain. So I've got a little schematic showing that. The graph shows results from an experiment performed in the 1960s. Now, this is where I'm being a little bit eccentric. I would rather show you the original first experiments, if you like, even though the graphics are a bit primitive, because I want to give due credit to the people who did this work in the early 1960s, which was really when all of this started. And they did some very interesting things. The graph shows the vertical strain, so not strain rate, vertical strain, as a function of time over nearly 2 years. So this chunk of snow was sitting there for 2 years or so, and The same experiment was done Camp Century, where it's about -22°C, at Bird Station, -25, and South Pole Station, -48. And you can see that after a while, the vertical strain rate, that's the gradient of this curve, settles down to a steady value for each sample. And we can look at that strain rate and think, how does this relate to the applied stress, which is different for each case, and other factors like the temperature of the experiment. It's important to note that actually for the first 100 days or so, in some cases, you can be getting this increasing value of the strain. So the strain rate is gradually decreasing. Okay, a confined compression test just means that you've got your snow block in a cylinder and you don't allow it to move sideways. And here again are some early results. Meller and Hendrickson were taking a lump of snow, putting it into a snow tube, and again looking at the strain rate over time. And they're shown in terms of the viscosity, which is why I was careful to explain to you about viscosity a bit earlier on, so that you're not going to panic at this. The really interesting thing about this, which was noted by Meller and Hendrickson, was that their results bore no resemblance whatsoever to the results found by Henri Barda from natural snow profiles. So here, very early on, is the first understanding that it's not enough to describe the snow just by its density. You've also got to know what the history of the snow has been, and that the lump of snow which is then worked on in the lab is not going to be necessarily the same as the lump of snow which has been subjected to the natural process of densification as it gets lower and lower in the snow profile. So Meller and Hendrickson were well aware of all of that. Well, obviously, lab tests have continued and they're still going on to this day. And the big advance, I would say, of the present day tests is that we have the possibility of using X-ray microcomputed tomography to look at the structure of the snow before and after a test. Now this is just a couple of examples just to show you the difference between a before and after sample, and comes from papers by, very recent papers by Lee and Baker, and they had the very good idea of taking samples from an ice core taken at Summit Station, Greenland, so that they have their dense snow has snow which has had the natural history rather than any kind of artificial history. So as far as possible, their samples are like natural snow. And there are an awful lot of results in that paper of great interest. The problem about lab experiments is that obviously they're a very powerful tool to look for our constitutive equation, but it's difficult to reproduce the spatial and time scales of natural densification processes. So it's very useful to complement them with field observations. It's been traditional to use density depth profiles to look at densification processes. They are the first and foremost source of natural data. If you've got a profile of density, rho, let's say, with depth, z, then you can calculate the stress on the snow element by integrating. So that's easy. The problem is to estimate the strain rate. And the only way to do this, if you've only got a density depth profile, is to assume something about the accumulation and then calculate the strain rate. And that's the weakness of this measurement, this method. It means that you have got to assume that you know what the accumulation is, and in practice that means you assume constant accumulation over the whole of the profile, which is certainly not necessarily true. However, we do at least have an awful lot of density depth profiles now. I recently sort of spent quite a lot of time trying to sort these out and grade them using all the profiles that I could find that were usable from the SumUp database. And I sorted them out into very high quality, which are red ones, through neutron probe profiles, which are black ones. And then we've got various grades of gravimetric profile depending on how good the data are. And I think now we do have data which cover the whole range of accumulation and mean annual temperature. So the climate conditions that we can find in the natural world. So that's a lot of data, but with a weakness. Now a quick diversion to, I thought I would pay tribute to an early career scientist, in fact, a master's student of the early 1960s, who did something which I find absolutely stunning. This is Scott Kane, who was a master's student at Ohio State. So what he did was build his own neutron probe, took it into the field during the Queen Maud traverse, and he obtained some very, very respectable density profiles, despite some really nasty and challenging physical conditions. Again, it's a rather difficult graph to look at, and you might have to stick your nose into the screen to see it. But basically, this is the classic line printer printout of a density curve with depth and density on the ordinate. He was able to see most of the features that you'd want to see in a depth density profile, despite the fact that he was actually struggling with the conditions. And he got 16 of these, which is pretty stunning. It was a very, very good effort indeed. Now, I don't know what happened to Scott Kane. I do know he was there with Fritz Kerner, and I do know that Fritz Kerner never mentioned this in all the years that I was working with him. So I can only suppose that there was a certain amount of rivalry between the neutron probe and Fritz, who was digging 10-meter pits and doing stratospheric studies. But there you go, there it is. And it was in the early 1960s. There was a bit of a revival of the neutron probe, started at the Institute of Hydrology in 1986, under much more pleasant conditions. This is my colleague Richard Harding. We went to the Hinterreisferne, and I'm stunned now to think that we managed to take a neutron probe all the way across Europe with nobody really batting an eyelid. And nobody having hysterics about radiation sources, but we did. Richard is actually doing a water count there in a dustbin, and obviously the sun is beating down and we're having a very nice time. The trick was to making this work was actually to automate it so that we could winch up the neutron probe source at a very slow speed, and therefore we could increase the spatial resolution by about 60 times. And once we did that, it was clear that we were going to be able to see an awful lot of detail in polar snow. And the little graph shows some profiles from Greenland, where you can quite clearly see the annual layering. We've done a profile over and over again, every 2 years, 4 years, and so on, so we can get successive profiles. And the key here is that once you are doing this slowly enough, then you can really see all the detail in the snow. Right, but nevertheless, the absolute prime data that we get as far as density, the depth profiles are concerned, comes from gamma profiling. And this is the RV gamma profiling, which has given us an awful lot of very, very high quality data. And with the detail that the gamma profile can give us, we can see the variations, the annual layering, the variations in density, but we can also see that these variations wax and wane according to the processes that are going on down through the profile. So this one from Berkner Island ice core, for example, shows first the large variation, then it dips down around about 550, yeah, well, perhaps a bit higher, kilograms per cubic meter, then it goes up again and goes down. And so you can get a very detailed glimpse into what the processes might be as the snow densifies. All right, that's density depth profiles. But what we would really like is to measure strain rate itself. And that can be done by finding some kind of marker in the snow and following it down. Bob Hawley and Ed Waddington developed a method of optical profiling and with an instrument that they put down a borehole. And you can see from this graph here that they're actually measuring directly the strain rate. I looked at the dates on this and I thought to myself that I think that Bob has started off an American for the first two and has turned into a Brit for the next two, but we're basically talking about a year or so between differences, and the months are a bit confusing there. This actually was a borehole in Devon Island, and there was a core taken, so we know the gravimetric density, and there was also neutron profiling, so we know the detailed density as well. So in that particular case, we've got measurements of strain rate and we've got measurements of density, which is what we want. Another method, if you like, of following a recognizable feature down through the snow as it descends is to use radar, and in particular phase sensitive radar can give us a tremendous amount of detail. These are some modern data which were collected by Elizabeth Case and Johnny Kinslake, and you can see that you've got a large number of profiles of compaction velocity across two ice rises in the Antarctic. Ideally, these measurements would be accompanied by density measurements, both to help interpret the radar data and also to give profiles of the vertical stress. But even so, it's terrific to have direct measurements of the strain rate. And lastly, we come to the classic coffee can experiments. Here you freeze a marker down into the snow at a certain depth and have a string or a wire which goes up to the surface, and you measure the amount by which the wire extends as the marker goes down. I think these are the first really good measurements which came from Rob Arthon. I've given the example of Berkner Island, but he did two other sites, I think. And you can see here in the coffee can experiment that the densification rate is certainly greater near the surface in the summer than in the winter. The weakness of this method is that the surface features, if you like, the surface processes carry on through down because you've always got your measurement made at the surface. And it would be nice to be able to subtract the 5 meter from the 10 meter and see what was going on between 5 and 10 meters. But even so, this led to some really good developments in the modeling. And finally, on this sort of brief run through all the data, there's the absolutely, no, not finally actually, but the classic and beautiful experiment which was done by Max Stevenson on South Pole. I think the paper is still in press or under review even, but he has some beautiful coffee can experiments, which again show this summer and winter change in densification rates, and which are going to be able to show a lot about the effect of temperature on densification. So to sum up, there is only one method really, which just the one method will give you everything you need, and that's the repeat neutron probe density profiles, because they will give you the stress, the strain rate, and also the change in density, which is actually sometimes, if you've got horizontal strain rates, not the same as the vertical strain rate. You can see from the diagram, we've got two measurements made 2 years apart, and the top is the density, the two densities, and the bottom one is actually the strain rate, with there being a variation in strain rate as well, which matches the variation in the densities. So this is a real difference in the strain, which goes not with depth, but with the actual density. Okay, so what's come out of all these data? Well, there are a whole tribe of macroscale models, the patriarch of which was derived by Heron and Langway, and this is the classic paper in 1980, Journal of Glaciology. What they did was take 17 profiles from Greenland and Antarctica, and they looked at the profiles and decided from those profiles that they could fit them with two expressions, one for the snow, which was less dense than 550 kilograms per meter, and another expression for the more dense snow. I've written the expressions in terms of the strain rate and the stress, so that you can see that the top one has a simple linear relationship, and that the viscosity of the snow is dependent on a density factor on a Arrhenius type expression with temperature. And also at the bottom, you can see I put a T. Now that was foolish of me because it looks like temperature. That's supposed to be time. It was Tor, and then I found I'd used Tors for something else. So this is a silly mistake, but that is time there, down at the bottom. And that is an indication that the viscosity of the snow is dependent on processes which occur over time, on its history. Similarly, if you look at the more dense snow, that has the expression depends on temperature. It has the same sort of dependence on density, but now there's also seems to be some kind of dependence on time and the stress. So that again is not an indication necessarily that the viscosity is dependent on the square root of the stress, but it is an indication that the history of the snow is important. These models have been incredibly successful as 1D models. So this is Heron and Langway and its children. They really work pretty well. There's a rational explanation for why there should be two stages, if you like, in the densification, which is that the deformation in the upper stage is to do with grain boundary sliding, and in the lower stage it's to do with plastic flow, grain deformation. There has been an assessment of the models, and into comparison, fern mice, and that shows it looked at six models, all of which were pretty well of that family, and it shows that predictions of the bubble close-off depth, which in this case is just the depth at which the snow reaches 815 kilograms per cubic meter, So it doesn't matter whether it is a bubble close off depth or not, it's just the density at that depth. The depth at that density. And it shows that all of these models over the whole range of temperature and accumulation that you might expect vary by about 2 to 8 meters. So that's really not a lot. And the models are actually pretty similar, although they serve slightly different purposes. For example, one of them is optimized to use output from a meteorological model, RACMO, so the world is doing a slightly different task to a model which is optimized using local measurements of temperature and accumulation. So they do well. However, I'm going to go on and point out a couple of things that we need to be aware of. If you take certain of the profiles and you plot them in a way which should show up deviation from the Heron and Lengway style equations, you can see that in some cases Heron and Lengway does not fit. What we're expecting is that if you plot this factor log rho over rho r minus rho against height or depth, that you will get two straight lines. You'll get a stage 1 straight line, which I've shown here in red, and a stage 2 straight line, which I've shown in blue. And that the data should fit those two lines with a transition point at 550 kilograms. Now, clearly these data from Pine Island Glacier don't do that. The stage 1 is okay. Stage 2 would be okay, the gradient is right, if we started at the right spot. So the implication is that the transition doesn't happen at the expected density, and what's more, it doesn't happen abruptly, it happens over a transition range. So what did I find when I looked at all the data I could get hold of? I found that the transition temperature increased with temperature, accumulation, and surface density, which is what I've tried to show in this diagram. And it can range from about 490 to 590 kilograms per cubic meter. This isn't actually a new idea. Again, the heroes of the 1960s, Charlie Benson in this case, spotted that this probably was the case. It certainly was put forward by Arno in 98. So it's not a new idea, but I think I've pinned down how the variation occurs a little bit more solidly here. So that's the transition density changing with changing climatic conditions. It's also the case that the width of the transition seems to change with accumulation. It's much more difficult to pin this down, but as far as I can see, at least after a certain amount of accumulation, you start getting a longer transition with more accumulation. And the numbers on this graph show the length of the transition zone in years, which varies from about 10 to 20 years. So that's two things. We have, in some cases, a non-abrupt transition, and it's not at the density we expect. Can we predict this? Can we find an equation for it? Well, I think we can. It's not very beautiful, but I argued that the grain boundary sliding could continue longer if the power law creep was more difficult to initiate. And that would mean that you'd expect the transition density to get higher if the difference between the two rates, K0 and K1 in Heron and Lengway style equations, increased, which there seems to do. And it also was quite interesting to observe that there seemed to be two groups of data separated by about 60 kilograms per cubic meter at the same value of K0 minus K1. And that rang a bell because I had been reading, with some difficulty, I have to say, a paper by Salamatin and co. Now, this was a microphysical constitutive equation, and it's basically consists of two parts: a grain boundary sliding expression, which is Richard Alley's 1987 expression, plus a power law creep expression, which I think is basically an Arnaud expression, but certainly has been worked through by Salamatin and his co-authors. And this is really, although complex, a very nice bit of work, because we have two physics-based, if you like, expressions for the two processes going on. And even if the solid geometry is a bit complex and it's all a bit hard to read, and even if you might say, well, are ice grains really spheres? If you leave it aside, what you have is also a key insight, at least for me it seemed like a key insight, which is that grain boundary sliding cannot occur unless there's a suitable space for the grain to slide into. There's got to be a void for the ice grain to be accepted into. And if not, the ice will actually dilate. So that if you want to have a confined situation, a one-dimensional situation in which your column of ice is not allowed to expand, the grains must be deformed in order to allow the basal sliding to occur. And this means that Salamatin was able to calculate how the two processes should merge one into another. So here on the left is his graph for Vostok, in which he shows various curves. If you look at the dashed curve labeled 1, that is the compression rate he expects and calculates for grain boundary sliding. The curve labeled 2 is the contribution from plastic deformation. And the proportion of each is given by the x fraction, which is on the dashed curve, which goes to the right. Those two contributions add up to make the total contribution of the compression rates. So you can see all of this happens over, say, 15 to 40 or so meters depth. When you look at the macro scale model with the non-abrupt transition, and my calculation for Vostok, I've got the compression rate declining. I've got the transition region defined by the vertical blue lines. And lo and behold, we've got the same transition region as the Salamatin calculations show. So I got quite excited at this because I thought, actually, I'm beginning to see what the microscopic explanation for my macroscopic equations are. And of course, I derived them only by fitting and a bit of good sense, if you like. Unfortunately, I can't go further than this because it's the only common site between all the sites that Salamatin produced data for and the sites that I've got. So until I can delve a bit deeper, I can't give you any more comparisons. But I think, obviously, for me, that's an exciting thing to look at. So that's topic number 1. Topic number 2 is the question of what happens if the horizontal strain rates are not 0. Well, it's fairly easy to see that if you squash the snow from the side for some reason, there will be increased densification, just as if you squash it from the top and the bottom. So you can start off by saying that that will happen if you've got horizontal divergence is negative, you get increased densification. If the horizontal divergence is positive, what will happen is the element will thin. Now, ice core chemists are quite used to this because they do this calculation for their ice cores, the stretching of the elements if the ice is moving outwards from their ice core. But there's also another thing to think about. Is there going to be an effect on the viscosity of the ice? Well, I thought, okay, let's have a look and truffle around in the old data and see what I can find. And I found some data from the Ross Ice Shelf project. This is from Crary and co, who were bombing around on the Ross Ice Shelf, doing all sorts of density profiles as best they could, and seismic data, and they have the climatic conditions. Now, Crary noticed that the density that he found at a common depth of 40 meters varied quite a lot over the Ross Ice Shelf, even though actually the climatic conditions don't vary very much. So he plotted this graph, which shows all these, on the ordinate, it shows the horizontal strain rate, and then he shows on the abscissa the density of the snow at 40 meters. So I thought it would be fun to calculate the density as it should be from Heron and Langway, and then adjust for the strain rate, which is what I did, and that's the red dots. So the negative horizontal strain rate I've pushed up, and the positive horizontal strain rates I've also pushed up because of vertical thinning, the density will be greater at 40 meters than it would otherwise have been. Now, it's by no means a perfect fit, and this is only a bit of fun because, first of all, I haven't taken into account horizontal velocity and where the snow has been. And secondly, the data aren't that good. It's not really worth busting a gut over it, but it's just entertaining, and it shows that, again, even in the early 60s, people were well aware that the horizontal divergence was going to be an important thing to correct for. Well, now, of course, we have absolutely beautiful maps of strain rate, surface strain rate, all over the Antarctic, for example. This one comes from Anika Hurlings and co, Ed Waddington involved as well, and it shows the ratio between the horizontal divergence and the downward strain rate. And the points where it's clearly blue are the points where you really do have to take notice of the fact that you've got horizontal strain going on and make a significant correction. So Anika and her team have done that for Greenland and for Antarctica. And as you might expect, the places you have to watch out for are on the ice shelves and on the ice streams coming down into them. Okay, so far so good. Nope, I've gone too far. I'm not too far, I think. No, I haven't. Right. I couldn't resist putting the infamous profile from upstream B into this talk because this is a point where Richard Alley actually showed that he had a tremendous feel for what was going on. And look, he looked at two sites with the same climate, same mean annual temperature and accumulation. Upstream B is on an ice stream and Camp BC is on a ridge. And he noticed that the densification rates were really different. And these data would get thrown out of modeling studies now because, you know, the accumulation rates are a bit uncertain. There was a nasty accident to upstream B in shipment and so on and so forth. But the point is that Richard spotted and proposed that the large longitudinal strain rates of upstream B implied that there were compression and tension forces in the snow which will decrease its creep viscosity. So this is an early comment on the fact that horizontal divergence could actually change the properties of the snow. And it's interesting that he can't prove that the two profiles started to deviate before 550, but there is a whiff of a sniff of the possibility. Right, so that's, of course, now, again, we have far, far better data to look at. And this comes from the Northeast Greenland ice stream. If you look at the picture on the left, you see a solid line, which is the observed firn thickness. And by that, the authors mean the depth at which the density reaches 830 kilograms per meter cubed. You can see that it changes really massively as they go across this ice stream with two dips on either side of the ice stream. Well, they make the correction. First of all, they predict what they think the depth should be using Heron and Langway, and that's the medium grey line. Then they make the correction for divergence, and that's the pale grey line. And you can see that there they're making corrections of up to 10 meters or so. So it is significant, but it's still not enough. And so what they've done is they've plotted the difference, how far are we out, against the net strain that they know that the profile has been subjected to over the last 400 years or so as the profile builds up. And you can see that they found that if the net strain is large, then the difference is large, all of which indicates that there's probably strain enhanced densification going on. And the differences here are up to 25 meters or so. So just to recap, we're talking here of about 25 meters. We're talking about 10 meters or so for the horizontal divergence. We're talking of up to 9 meters or so for getting things wrong with that transition. And we're talking about 2 to 8 meters wrong or difference between the various macroscopic models. So in these particular places, this is serious stuff. Well, what to do? A very nice idea from Folk Orszewski co-workers was to see whether you could correct with a simple correction factor for the strain softening. So something easy to do, which means that you can still use your Heron and Langway style modeling. And the answer is yes, you can. And he's shown a very nice little graph showing the thinning in the Antarctic. And again, it's going up to about 30 meters, which is about the same as in the Greenland example. And again, it's happening on the ice shelves and the ice streams. However, there is a snag, which Folk pointed out. If the Heron and Langway style model has been calibrated using data from one of these places where you've got quite high levels of strain softening, then the correction is going to go wrong. So in an ideal world, what we would do would be to recalibrate the models using data where there isn't any strain softening, and then apply the correction factor. So that's really a housekeeping task. Okay, coming towards the end now. I started off by showing you the sort of equations that we wanted, which were three-dimensional equations, because as I think I've sort of indicated, there are situations where we do need to think about the 3D situation. And that's because all the components of the stress applied on the snow might influence its viscosity. Well, we do have actually a fairly simple, or at least to my mind, expression, which was developed by Gagliardi and Meissonier to deal with a rather nasty situation at the top of the Dôme de Goûter, where they needed to look in 3D. There are relations between the strain rate and the strain tensor, which depend on a temperature factor, which is in the capital B part of all this, on the effective strain, the effective stress, and some exponent n, which might be 3 or 4, but also two factors which really describe how porous the snow is. So for ice, A is going to be 1 and B is going to be 0, and for snow, as the density changes, A and B are going to change. Now, I'm not quite sure whether this is the latest derivation of the A and B factors. It's what I found. If so, I'd say it could do with a bit more data from the modern experiments and from other profiles. But I might be misjudging the authors because they may have done a lot more that I'm unaware of. But this seems to me to be the most promising way to get a fairly simple equation which can be used where strain softening is going to be a problem. So that's about it. I think my conclusion really on the where are we now is, of course, there are going to be there's more work going on at the moment. Things are going on in the field. There's the Taylor Dome project. There are many ongoing projects. There are laboratory experiments ongoing, and they will bring in new ideas and data. And I'm sure there are things in the pipeline that I don't know about. But I'd like to end with the suggestion that it's time for a bit of housekeeping. To take stock, if you like. Wouldn't it be useful if we had an agreed set of high quality field data for common use to use for intercomparison of models, which we don't have at the moment? The fern mice intercomparison study made an excellent start, but it didn't actually compare simulations to field observations. Wouldn't this be the next step? I think rerunning key studies on common data would cast light on processes, especially what I'm interested in, which is the transition from grain boundary sliding to parallel creep, and also perhaps could add more to the Elmer ice model. Should we re-optimize the parameters of models? For example, Tim Schultz conducted a very careful assessment of the alley stage 1 equation using new data from SumUp, but he used a density cutoff at 540 kilograms per cubic meter. Should we perhaps have a look at that again, using a lower cutoff so that we know that we're not involving any part of the transition region? The Heron and Langway style models all should be purged, if you like, the data that's used to calibrate them, to make sure that we're excluding effects of transition and horizontal strain. All of this is perhaps a little bit boring, but it's the classic sort of thing that you do with international intercomparison projects. And I'd like to think that perhaps that's one of the things that we could think about trying to set up. So that's it. I hope that hasn't been too boring for those that know all about snow. It's great stuff. You know, you can't spend a happier day than digging the snow pit and looking at snow. And I've certainly greatly enjoyed my time working in the field. Thank you.
Thank you very much indeed, Liz. I've a number of times considered myself to be best described as a professor of digging in various places in Antarctica. So the way that we usually do questions is we ask people to indicate on the chat if they have a question for Liz, and then you can unmute yourself and ask a question directly. I've got my eye on Facebook. I don't see anything there yet. But are there any questions from the audience for Liz? I have to say it was lovely to actually finally see what you were using the neutron probe for. I used one during my PhD for measuring till water contents. I have heard you talking about using them a number of times, but I've never heard before what it is that you're actually using them for. So that was really useful for me. I'm assuming that we can't actually use them anymore. I assume that they're no longer considered to be good instruments, or are people still using them?
Oh, well, you touched me on a fairly sore point. At the moment, there's a project going ahead on the summit of Greenland where the cosmic ray physicists, bless them, are going to drill about 100 holes or so to install a cosmic ray telescope, if you like, in the ice. And they've announced that they would like to have the density to 1%. So the drilling is actually not going to be core drilling. It's going to be using the Bass ray drill, which basically minces up the ice and spews it out. So the idea is to use the probe to do the density profiling, which is all very nice, and I'm all very excited about this, apart from the fact that when we got the probe to Heathrow, it came back about 5 minutes later with improper labels and we don't like this, etc., etc. So the paperwork is turning out to be a little bit grim at the moment. I don't want to moan, but one of the side effects of Brexit has been that Greenland is no longer in Europe. No, sorry, we are no longer in Europe. We have been cut off from the continent, and you know, one of the side effects is that moving radioactive sources has become an awful lot more difficult than it was.
I don't think it was ever easy. I do remember shipping a neutron probe to Norway during my own PhD. Paco has a more sensible question, I think. Let's go ahead now.
Yes. Well, congratulations for this nice talk. It was really interesting. And I have my question is related to this high quality data set that you mentioned for this intercomparison experiment. Taking into account the available data, presently available data, which kind of data do you think is the most important missing data that should be complementing the existing data?
Well, if you think about new data, I think measurements of strain rate and density profiles are the ones that we don't have enough of. If we're just talking, I think an awful lot can be done with depth and density profiles, but over the years, different people have used different data sets. So, for example, there seems to be very little overlap between the data that was used by Salamatin and co. and the data which are in SumUp. And so I think just on a very simple level, it would be nice to say, right, these are the data we would like everybody to use. You know, they can use other data, but can they please use this core data as well, so that we have the opportunity to compare between different models and different groups.
Okay, thanks.
Yeah.
Phil Anderson, do you have a question?
Fantastic overview, Liz. I'm always impressed by your talks, and never more than just now. Thank you very much. One thing, as an atmospheric chap, I'm thinking about catabatics. You're going to have a correlation with slope. Slope means you're getting your spreading outness, and that's a problem, but you're also going to get your catabatics there, which will enhance the ventilation of the firm. Has that really been taken out and accounted for, or is that perhaps a blind spot with still between the atmosphere and the glaciologists not talking to each other as much as we should do?
Well, I certainly don't think we talk enough together, Phil. I think you're right. As far as I know, the catabatics and general surface wind effects are in the latest version of Snowpack, which is being used by Nanda Weaver. So they are in the models. I certainly didn't correct, if you like, for catabatics, and you're quite right, it's a blind spot. So yeah, that's another thing to go back and look at.
And Roger, I think you have a question. Would you like to unmute yourself?
Yeah, thanks very much. Thanks for the talk, Liz. The grain boundary sliding to plastic transition, you described it in as expressed in a number of things. Do you have a sense of how it's expressed in things like Young's modulus and maybe seismic P and S velocities?
Oh, I think the honest answer is no, I don't, I'm afraid. I can think about it, but no, you caught me.
No worries. It's just I'm the opposite end of the spectrum. I mean, I'm just field geophysics and observation, and we're starting to get together decent P wave and even S wave velocity and attenuation observations in the fern, but trying to relate it back to any physics that's going on in the fern structure. Needs insights and of the mechanisms and so on that you and your colleagues have, and marrying them together is going to be interesting. We certainly see a change in the Young's modulus behavior and the relative speeds of P and S, for example, at different depths. And for all that we're happy with our observational data, what does it actually mean? It's the usual plea. But yeah, thanks for that. That's given us some interesting things to think about.
Okay, I think we've run out of questions there, unless anyone has a last question for Liz. So it brings us to reminding you of next week's seminar, for which I don't actually have a slide, although I did try and get one. Next week we have Joe Cook, Ian Stevens, Lou Chevalier, Shuang Feng, and other early career scientists of the Deep Purple project, talking about albedo changes on the Greenland ice sheet and the implications for mass balance. I always think the Deep Purple project sounds like a heavy metal band, but it's Martin Tranter's big project looking at microbial albedo changes on the Greenland ice sheet. So hopefully see you all here next week. And a huge thank you to Liz for a really great seminar today. So thank you very much indeed. And thanks to everyone for coming along.
Thank you. Bye.